As the global population continues to grow, so does our demand for energy. Traditional fossil fuels, while effective, come with significant environmental costs, including air pollution and greenhouse gas emissions. This has led to an urgent need for cleaner, renewable energy sources. Wind energy has emerged as a leading solution, but how exactly do wind turbines convert wind into usable electricity? Today, we're going to unravel the mystery behind wind turbines, exploring their inner workings, the technology that makes them so efficient, and why they are crucial for our sustainable future. The physics of wind energy. Before delving into the mechanics of wind turbines, it's essential to understand the fundamental source of their power: wind. Wind is essentially moving air caused by differences in atmospheric pressure. These pressure differences arise from uneven heating of the atmosphere by the sun, irregularities of the Earth's surface, the rotation of the Earth. As air moves from high-pressure areas to low-pressure areas, we experience wind. The strength of the wind depends on the magnitude of the pressure difference. Let's examine each component of a wind turbine in more detail. 1. Blades. Wind turbine blades are marvels of aerodynamic engineering. They're designed to capture the maximum amount of wind energy while withstanding extreme forces. Modern blades are typically made from composite materials like fiberglass and carbon fiber, which offer an optimal balance of strength and weight. The shape of the blade is crucial. It's based on airfoil principles similar to airplane wings. As wind flows over the blade, it creates areas of high and low pressure, generating lift that causes the rotor to spin. Blade design considerations include length. Longer blades capture more wind but are heavier and more difficult to transport. Twist. Blades are twisted to maintain an optimal angle of attack along their length. Tip-speed ratio. The ratio of the speed of the blade tip to the wind speed, typically optimized around 7:1. 2. Rotor. The rotor consists of the blades and the hub to which they're attached. It's responsible for converting the linear motion of the wind into rotational energy. The size of the rotor directly affects the amount of energy that can be captured. Larger rotors can capture more energy, but also face greater structural challenges. 3. Nacelle. The nacelle houses most of the turbine's mechanical and electrical components. It's typically made of fiberglass and can be as large as a small bus. Key components inside the nacelle include the generator, gearbox, in some designs, brake systems, control systems, cooling systems. The nacelle is mounted on a yaw system that allows it to rotate and face the wind for optimal energy capture. 4. Tower. The tower supports the nacelle and rotor, elevating them to heights where wind speeds are stronger and more consistent. Modern utility-scale wind turbines can have towers over 100 meters tall. Towers are typically made of steel, either in a tubular or lattice structure. Tower height is a crucial factor in wind turbine efficiency. Wind speed generally increases with height above the ground, a phenomenon known as wind shear. The relationship between height and wind speed is often modeled using the power law. 5. Generator. The generator is where mechanical energy is converted into electrical energy. Most wind turbines use either induction generators or permanent magnet generators. Induction generators are robust and cost-effective, but require a gearbox to increase the rotation speed. Permanent magnet generators can operate at lower speeds, allowing for direct drive systems that eliminate the need for a gearbox. 6. Gearbox. In turbines that use them, gearboxes play a crucial role in increasing the rotation speed from the rotor, typically 5 to 20 RPM, to the speed required by the generator, typically 750 to 3,600 RPM. Gearboxes are complex and can be a source of maintenance issues, which is why some modern designs opt for direct drive systems. 7. Control systems. Modern wind turbines are highly automated, with sophisticated control systems that adjust blade pitch to optimize energy capture and prevent overloading, control yaw to keep the turbine facing into the wind, monitor wind speed and direction, regulate power output, implement safety protocols, including emergency shutdowns. The wind energy conversion process. A deeper dive. Let's explore each step of the wind energy conversion process in more detail. Step 1. Wind detection and turbine positioning. Wind turbines use anemometers to measure wind speed and wind vanes to determine wind direction. This data is fed into the turbine's control system, which adjusts the yaw of the nacelle to face the wind. The yaw system typically consists of a series of motors that rotate the nacelle on a large bearing. The control system also adjusts the pitch of the blades, their angle relative to the wind. This allows the turbine to optimize energy capture in low winds and prevent overloading in high winds. Step 2. Blade rotation. As wind flows over the blades, it creates a pressure difference between the upper and lower surfaces, similar to an airplane wing. This generates lift, causing the blades to rotate. The amount of lift generated depends on several factors: wind speed, air density, blade shape and size, angle of attack, the angle between the blade and the relative wind direction. The blade's design is optimized to maintain the most efficient angle of attack along its entire length, which is why turbine blades are twisted. Step 3. Rotor shaft rotation. As the blades rotate, they turn the rotor shaft. This low-speed shaft typically rotates at about 30 to 60 RPM. The kinetic energy of the wind has now been converted into rotational mechanical energy. Step 4. Gearbox operation. In turbines that use gearboxes, the low-speed shaft connects to the gearbox. The gearbox uses a series of gears to increase the rotation speed, typically by a factor of about 90. This means that if the rotor shaft is turning at 30 RPM, the high-speed shaft coming out of the gearbox will be turning at about 2,700 RPM. Gearboxes are complex and can be a source of maintenance issues. They require regular lubrication and can suffer from wear and tear due to the high forces involved. Step 5. Generator operation. The high-speed shaft drives the generator. In an induction generator, which is commonly used in wind turbines, the shaft spins a rotor inside a stator. The rotor contains a series of magnets, while the stator contains coils of wire. As the magnets pass the coils, they induce an electric current, a process known as electromagnetic induction. The frequency of the generated electricity depends on the rotation speed and the number of pole pairs in the generator. For a typical 4-pole generator to produce 60 Hz electricity, standard in the US, it needs to rotate at 1,800 RPM. Step 6. Power conversion. The electricity produced by the generator is typically 3-phase alternating current, AC. However, its frequency and voltage may not match grid requirements. Power electronic converters, consisting of rectifiers and inverters, are used to convert the generator output to grid-compatible AC. These converters also allow for variable speed operation of the turbine, improving efficiency across a range of wind speeds. Step 7. Transformer step-up. Before the electricity can be transmitted to the grid, its voltage needs to be increased to reduce transmission losses. A step-up transformer, located either in the nacelle or at the base of the turbine, increases the voltage from around 700 volts to tens of thousands of volts. Step 8. Grid connection. The high-voltage electricity is then sent via underground cables to a substation. At the substation, the electricity from multiple turbines is collected and may be further stepped up in voltage before being fed into the power grid. Advanced wind turbine technologies. As wind energy technology continues to evolve, several advanced concepts are being developed or implemented. 1. Floating offshore wind turbines. These are designed for deep water where fixed bottom turbines are not feasible. They use various floating platform designs, including Spar-buoy, a long, slender cylinder that extends deep into the water; semi-submersible, a platform with ballasted, watertight pontoons; tension leg platform, a floating platform anchored to the seabed with tensioned mooring lines. Floating turbines open up vast new areas for wind energy development, particularly in countries with deep coastal waters. 2. Airborne wind energy systems. These systems aim to harness the stronger, more consistent winds found at higher altitudes. Concepts include kite-based systems that fly in figure-8 patterns, pulling a tether connected to a ground-based generator; rigid wing systems that generate electricity on board and transmit it down a tether. While still in the development stage, these systems could potentially access wind resources not available to conventional turbines. 3. Bladeless wind turbines. These innovative designs aim to generate electricity without rotating blades. One concept uses a tall, oscillating cylinder that vibrates as wind passes around it. This vibration is then converted into electricity. Potential advantages include reduced visual impact, lower noise, and less danger to birds. 4. Smart wind turbines. Modern wind turbines are increasingly incorporating advanced sensors, data analytics, and machine learning algorithms. These smart turbines can predict maintenance needs, reducing downtime and repair costs, optimize performance based on weather forecasts and historical data, coordinate with other turbines in a wind farm to maximize overall output. Environmental and ecological considerations. While wind energy is clean and renewable, it's not without environmental impacts. 1. Wildlife impacts. Birds and bats can collide with turbine blades, leading to fatalities. However, modern turbines are designed to minimize this risk. Slower blade rotation speeds, larger blades that are more visible, sighting turbines away from major migration routes, using radar to detect large flocks, and temporarily shutting down turbines. Studies have shown that wind turbines contribute to far fewer bird deaths than other human activities such as buildings, vehicles, and domestic cats. 2. Noise. Wind turbines produce two types of noise: mechanical noise from the generator and gearbox, aerodynamic noise from the blades moving through the air. Modern turbine designs have significantly reduced mechanical noise. Aerodynamic noise remains a concern for some nearby residents, although it's generally not loud enough to cause hearing damage. 3. Visual impact. The visual impact of wind turbines is subjective. While some find them to be eyesores, others see them as symbols of clean energy. Offshore wind farms can mitigate this issue by being located far from shore. 4. Land use. While wind farms occupy large areas, the actual footprint of turbines and access roads is relatively small. The land between turbines can often still be used for agriculture or grazing. The future of wind energy. The wind energy sector is poised for significant growth and innovation. 1. Increasing turbine size. Turbine sizes have been steadily increasing, with offshore turbines now reaching capacities of 12 to 14 MW and rotor diameters over 220 meters. Larger turbines can capture more energy and reduce the cost per megawatt hour of electricity produced. 2. Improve materials. Research into advanced materials could lead to longer, lighter blades and taller towers. Carbon fiber composites, for example, could allow for blades over 100 meters long. 3. Energy storage integration. To address the intermittency of wind power, wind farms are increasingly being paired with energy storage systems. These can include batteries, pumped hydro storage, or even hydrogen production through electrolysis. 4. Artificial intelligence and machine learning. AI and ML algorithms are being used to optimize wind farm layouts, predict wind patterns, and improve turbine performance and maintenance schedules. 5. Recycling and sustainability. As the first generation of wind turbines reaches the end of its lifespan, the industry is focusing on recycling and sustainable decommissioning. Research is ongoing into recyclable blade materials and more efficient recycling processes. Conclusion. Wind turbines represent a fascinating convergence of aerodynamics, mechanical engineering, electrical engineering, and environmental science. From the careful design of their blades to capture the maximum amount of wind energy, to the sophisticated control systems that optimize their performance, these machines are a testament to human ingenuity in the quest for sustainable energy. As we continue to face the challenges of climate change and seek to reduce our reliance on fossil fuels, wind energy will undoubtedly play an increasingly important role in our global energy mix. The ongoing advancements in wind turbine technology, from larger, more efficient designs to innovative concepts like floating offshore turbines and airborne wind energy systems, promise to make wind power an even more viable and cost-effective energy source in the future. Understanding the intricacies of how wind turbines work not only satisfies our scientific curiosity, but also helps us appreciate the complexity and potential of this clean energy technology. As we move towards a more sustainable future, wind turbines will stand as towering symbols of our commitment to harnessing the power of nature in a way that preserves our planet for future generations.